Hello everyone, I'm Nitin Reddy from EC department. My topic is scheduling wireless virtual networks functions. Network function virtualization promises to reduce the cost to deploy the operate large networks by migrating network functions from dedicated hardware appliance to software instance running on general purpose virtualized networking and computing infrastructures. This in time shall improve the flexibility and the scalability of mobile networks in that deployment of new applications and services will be quicker and different network functions can share the same resources, paving the way to further economics of scale. This progressive process of network softwareization is set to play a pivotal role in fifth generation mobile networks. In this context, the network as a service business model shall allow operators to tap into new revenue streams by further abstracting the physical network into service-specific slices, possibly operated by different mobile virtual network operators. The envisioned vertical applications range from high-definition video delivery to machine applications. Implementation. We implement the VNF placement and scheduling solution presented in this work is in a proof of concept, NFV management and orchestration framework, named Empower. Notice that the prototype currently supports only wireless access networks based on the 802.1 family of standards, and as a consequence, applications considered described in the next section target enterprises, VLANs, and campus network scenarios. Nevertheless, as seen in the previous section, the provisioning model does not make any assumption about the particular link layer technology and can be well applied to any kind of radio access, including OFDMA networks such as LTE and TLT advanced. Our proof of concept is loosely modeled after the TSSA reference NFV architecture. The architecture is conceptually divided into three layers. The bottom layer consists of a physical as well as the virtualized resources composing the NFVI. The architecture is conceptually divided into three layers. The bottom layer consists of the physical as well as the virtualized resources composing the NFVI. In the second layer, we have the actual VNFs, which are the software implementations of a particular network function capable of being executed over the NFVI. We remind the reader that in this work also radio access is treated as a VNF. Finally, in the third layer, we have the operational support systems and the business support systems used by the network administrators to operate and manage their virtual networks. The management and orchestration plan covers the orchestration and the management of physical and or virtual resources that support the NFV as well as its life cycle management of VNFs, that is creation, configuration, monitoring, and destruction. Our architecture currently accounts for three kinds of NFVI resources, namely basic forwarding nodes, packet processing nodes, and radio access nodes. The latter, in addition to the features supported by the packet processing node, also embeds specialized hardware in the form of one or more 802.11 wireless NICs. Figure 11 sketches the system architecture we name wireless termination points, the physical points of attachment in the RAN, supporting virtualized radio processing capabilities. Conversely, the click packet processors are the forwarding nodes with computational capacity. These nodes are essentially programmable switches running an embedded version of Linux and capable of performing arbitrary operations in the traffic, example load balancing, firewalling, deep packet inspection, etc. As the name suggests, the actual packet processing is performed by multiple instances of click modular router. Click allows build complex VNFs using simple and reusable components called elements. Click includes over 300 elements supporting functions such as packet classification, access control, deep packet inspection. Elements can be composed in order to realize complex VNFs. Finally, click can be easily extended with the custom processing elements, making it possible to support features that are not provided by the standard element. Virtual infrastructure managers. As virtual infrastructure managers, we use a combination of frameworks. RYU is used to configure the switching fabric, while for the NFVI we extended the Empower controller presented by the authors in order to support also the generalized packet processing nodes. The controller supports multiple slices on top of the same physical infrastructure. A slice is a virtual network with its own set of WTP, WTP, WTPs and CPPs. The controller is responsible for deploying VNFs on the network devices. Orchestrator. From the architectural standpoint, the VNF placement algorithm resides in the orchestrator, which is in charge of deciding whether a particular request can be accepted or if it is must be refused. If a request is accepted, then the orchestrator is in charge of mapping the request onto substrate network. That is, network resources must be allocated and configured on both the substrate node and the substrate links, and the VNFs must be instantiated on the selected nodes. Notice how our proof of concept does not impose a specific orchestrator, leaving network administrators free to use other currently available solutions such as OpenBattery. Applications: radio access network slicing. In this use case, we aim at demonstrating the performance isolation features enabled by our joint VNF placements and scheduling solution, such as such use case is supported by introducing a Mac hypervisor implementing the slice scheduling techniques described in the previous section. The internal architecture of a radio access node. Notice how not the entire Wi-Fi MAC is virtualized. More precisely, Wi-Fi controls frames generation as well as the actual physical layer are not virtualized due to their tight timing computational constraints. On the other hand, each tenant can have its own radio resource management instance as well as its own management place. In this work with RRM, we refer to wireless client scheduling that to rate adaptation, which can be defined on a per tenant basis too. For example, one tenant can use a wireless station scheduler aimed at ensuring fairness, while another tenant could opt for a scheduler aimed at improving the aggregated slice bandwidth. Data or management plane offloading. Wireless and in particular mobile network have been so far designed around the requirement of the downlink. Signal strength measurements in the recent years, however, we have witnessed a mushrooming of new uplinks and applications such as machine type communications, Internet of Things, and vehicle of infrastructure. Applications such as machine type communications, Internet of Things, and vehicle of infrastructure as well as the symmetric mobile applications. This calls for a paradigmic shift where the traffic originated from a wireless client is received by one node after the traffic destinated to the same client is transmitted by another node. This kind of network setup is usually referred to as uplink, downlink, decoupling, and in its most general form can consist of two possibly non-overlapping sets of transmitting and receiving nodes. Conclusion. NFV is rapidly emerging as a flexible solution to deploy and operate future mobile networks. However, in order to fully deliver on its promises, the concept of NFV must be extended also to the radio access segment of the mobile network. This paper we tackled this challenge by presenting a novel formulation of the VNF placements problem composing also radio access VNF. We then introduced a ILP based algorithm for small networks such as scalable heuristic named PINE for large deployments. Numerical simulations showed that the proposed heuristic and can approximate the performance of the ILP based placement algorithms for realistic substrate networks. Finally, we reported on a preliminary proof of concept implementations of NFV management and orchestration framework for enterprise VLNS. Thank you.